Welcome back to Algebra 2. Today we're going to speak further about solving quadratic equations by taking the square root of both sides. But this time we'll talk a little bit about an odd wrinkle. What do you do when the square root on the left side, x squared, is equal to a negative number? What do you do there? We'll take a look at that now. It's really cool to be able to talk about this because it introduces us to a special kind of math humor. We know what the right symbol is, that's pi. The left symbol, that I, is the subject of today's math lesson. Hopefully you will start getting this math joke and laughing perhaps even in the next week or so. So here's our example. We'll take x squared plus 1 is 0. We're going to try to solve this by taking square roots. Well, we follow our steps and x is equal to plus or minus the root of negative 1. We've learned for years that you only take the square roots of positive numbers. You can't take the square root of a negative number. What do you do here? Well, in order to solve this kind of a problem, we need a different kind of number. And that number is going to be an imaginary unit. I attached a video to this assignment by Welch Labs that introduces the whole idea of the imaginary unit. Interesting video. I suggest you watch it. It gives a little bit of context behind why these imaginary units became developed. The imaginary unit, I, that's the square root of negative 1. So the I equals root negative 1, and I squared equals negative 1. Remember when we talked yesterday how the root of a smiley face times the root of a smiley face equals a smiley face? Well, the root of negative 1 times the root of negative 1, is going to equal to negative 1. So I is root negative 1. I squared is negative 1. You want to keep track of these exponents. We'll talk more about that probably in our next lesson. Because if I squared equals negative 1, I to the fourth would equal negative 1 times negative 1, which would just equal 1. So we have to keep track of exponents. That'll be more for tomorrow's lesson. How could we, how do we work with this? Well, if we have root negative 9, this looks really odd, but the process is actually quite simple. If we want to get rid of that negative sign, we can rewrite it so. We can say root 9 times root negative 1. Root 9 is 3, and root negative 1 is I. We can write our answer as 3i. If we want to write it a little bit differently, I could just say, hey, root 9, or root negative 9, I could just say this equals I times root 9, which equals 3i. To get rid of that negative sign, I can just move this negative out and put an I in front, and I've simplified it. I still have to simplify my radical, but that's all I have to do in order to get rid of that negative number under the radical sign. Take a look at root negative 12. How will we do this? Well, root negative 12 is going to equal to root negative 1. We'll take that, and we're going to end up making that just I times 2 squared times 3. I've got a prime factorization of 12 there. This 2 squared, since I've got 2 of the same factor under the radical sign, there's a jailbreak, and this 2 comes out. That's how I get the 2 out here. This negative 1, root negative 1, that's simply my I, so I can rewrite this as 2i root 3. And there we have it. Let's look at some of the mathematical rules for how we handle this. If x squared equals k, so we'll have x squared equals 16, for example, and k is greater than 0, then x would be equal to plus or minus root 16. X is equal to plus or minus 4 if x is greater than 0. However, if x is equal to 0, then there's only one real solution because you don't have a square root of 0. 0 times 0 is just 0. But if k is less than 0, then you're going to have two complex solutions. So if you were to have x squared, equals negative 16, then I would say x will be equal to negative root 16, and then I would say x will be equal to I root 16, which is equal to 4I, plus or minus 4I. There we have it. Because if k is less than 0, they'll have two complex solutions, positive 4I and negative 4I. What's with the absolute value bar underneath the radical? Once I've taken the negative root out by I, I'm left with a positive number under the radical sign. So the radicand has to be positive when I'm dealing with these complex solutions. Notice my answer will always be expressed in a whole number, and then I, and then any kind of radical that would come after that. Let's try one. Z squared plus 45 is 0. I'll rewrite this. Z squared is negative 45. I'm going to take the square root of both sides now. So z is going to be equal to plus or minus root negative 45. First thing I have to do here, I want to get that I out. Now I've got a positive root. I've got this imaginary unit, this root negative 1. I've gotten that out. Now I'm dealing with root 45. We can simplify that because 45 factors are 9 times 5. 9 is a perfect square, so I can take the square root of 9, be 3. I'm left with plus or minus 3I times root 5. Let's try this one. How are we going to do this? Well, first, I'm going to simplify. Take this negative, take this 10, take it over to the right side. So 2 times the value w plus 3 squared equals negative 8. Now I'm going to isolate that value being squared on the left-hand side. So I'm going to divide both sides by 2. Now I'll take the square of both sides. W plus 3 equals plus or minus root negative 4. I'm going to isolate the w now. In just a minute, I will actually. Negative 4, I'm going to root negative 4. I'll take the I out, so I'm left with just root 4, which will be equal to plus or minus 2I. And then w is negative 3 plus or minus 2I. So this is the way you have to write your answers, your whole number plus or minus your imaginary number. All right, I'm going to give you some more practice for tonight, working off of questions with page 200 on page 204, taking square roots. These questions this time will be involving imaginary units. So on page 204, answers questions 5 through 7 and 9 through 12, 14 and 15, and 16 and 17. And look forward to hearing what you think about imaginary units in the wonderful world of complex numbers. See you later in class.